Good afternoon. This morning is going to be a tough act to follow. I hope, though, that we'll be able to come back to earth in political decision-making. And the last part of this week, we want to spend on examining some of the science policy links, the decision-making that is happening between climate change and what we know, what the scientists know, and what the politicians think they should or might want to do about it. My own background, I studied in England and London, later on in Canada, biology and agriculture. So many of the examples that I will be presenting have to do with the effects of climate change, of temperature change, particularly on different organisms, on crop production, on trees, and what it means for agricultural productivity and for the life-sustaining mechanisms on Earth to go through climate change and to go through temperature increases. And the point of departure is the pronouncement of the convention meeting in Paris that said we think that 1.5 degrees is a safer limit than 2 degrees. Now, the 2-degree limit was already pronounced in the late 80s. 30 years ago, scientists said and realized there's a temperature change happening, and they said in the late 80s that if we go much beyond 2 degrees on average temperatures, we will be in deep trouble. So it's been a long time that the 2-degree limit exists, and only recently, a year and a half ago, that discussion has entered into politics. Now, the reason why I'm talking about the interface of science and politics is because for the last 12 years of my life, I was director of an international organization that deals with climate change and global change, the IAI, which is one of the co-organizers of this event. And since last month, I'm a free man. I've left the IAI and can do as I please. And this was one of the commitments that still stand. And I think it's very important, as I said this morning in the comments already, if the world wants to implement change, the way to get that change to happen is through you, through the people who realize that something needs to be done and who have the scientific and intellectual tools to do something. So I think these events of these last 2 weeks are extremely critical for a sane future development of the world. Now, first of all, I will just simply give you material that comes straight out of the convention, out of the groups of scientists that have analyzed what the convention is all about, and that gives you a little bit of background on the policy considerations and scientific consideration beyond that discussion to 1.5 degrees. After that introduction, Inés will bring you up to speed on climate and how climate functions and how it fits into the picture of climate change and what that means for the political discourse. And then after a coffee break, I will come back and give you some of the ideas of the effects of climate on ecosystems, on production systems, and so on. So the first series of slides are key messages that come out of the United Nations conventions, structured expert dialogue. They are very good at inventing these nice words. So there is a group of experts that came together and pronounced on the merits of having these limits. First of all, to have a long-term goal is good. If you don't have a goal, you have nowhere to go. So you need to define where you want to set the limits to climate change. And the group came to the conclusion that we need to define a temperature limit. One could have done something else. One could have defined a CO2 limit. One could have defined an economic impact limit. One could have defined the limits by insurance premiums or any other number of things. And the critical indicator, and that's why we keep talking about temperature, the critical indicator is temperature because many things depend on temperature. That's not a linear process. 1.5 degrees or 2 degrees or even 4 degrees of temperature increase is what we all experienced this morning between 8 o'clock and 8:15. It's nothing. It's totally normal. In the diurnal variations of temperatures, a change in 1.5 degrees is irrelevant. But as a global mean, it suddenly becomes relevant and gets a different meaning. There is a perception, or there was a perception, that if we can just stay below that limit, nothing will happen. That's out of the window. That's very clearly out of the window. We already have climate change. We already see the effects. So there is no guardrail. That's a very important conclusion, even today with 0.8 degree global average change, and much more than that in some regions. We are seeing very considerable impact of climate change on agricultural production, on the incidence of disasters, on insurance payouts, on flooding events, and so on and so on. There are phenomena in climate now that didn't exist 50 years ago. So it is not a guardrail, it's an intellectual construct to set some kind of a limit, and part of this afternoon's task will be to see whether that limit is sensible or not. And that implies risk assessments, but also value judgments. Now, I use risk as the probability of something to happen and the severity of the consequences of something to happen. It's a very approximate definition of risk, but different societies are willing to take different levels of risk. Some societies are very well prepared to deal with risk. Others just cope. Bangladesh has been flooded for the last 30, 40, 50 years, almost on an annual basis, and they somehow manage. Buenos Aires sees floods and has been seeing floods for a very long time. We've seen the disasters around Rio de Janeiro basically since the 70s and 80s. Every time it rains, there is a mountain coming down, and people keep going up there, constructing their houses to come down yet again a few years later. In Venezuela, the large disaster that happened on the coast of Venezuela a few years back, the same path of mud and rock flow was already there in the 50s when the last time major rains caused a disaster. So these societies, different societies, adapt to risk in different ways, or don't adapt and just cope with it more likely. So regional and local levels are extremely important in this discussion. What do we want to accept in terms of risks, and how do we value it? So national circumstances are important. We're all aware that under America First policy, the US has pulled out of the Paris Agreement. Probably that's not even relevant because all the states within the states stay with the agreement. So what the federal government says has some impact, but it's not nearly the disastrous result that it might be. In terms of mitigation, there's two ways to look at climate change. Mitigation, which is in the lingo of the convention, the ways to reduce carbon dioxide or greenhouse gas emissions, and thereby reduce the effects of greenhouse gases and mitigate the rise in temperature. That is the definition that comes out of the convention. It's very important to realize that because other people use mitigation in a very different context. You can mitigate the impact of climate change by changing your agriculture or something like this. The convention uses a different definition and this specific definition of mitigation. The rest is adaptation. Now, 10 years ago, adaptation was a taboo word. There were actually governments in the Western democracies whose representatives were not permitted to use the word adaptation in the context of climate change because it looked like a definition of defeat, that we can't mitigate enough, and therefore we now need to adapt, and we don't want to admit to that weakness. Now it is very clear climate change is with us, and adaptation is important. We know how to mitigate, reduce carbon emissions. It's not easy. It's got industrial components. It has technological components. It has psychological components. Some of what we heard this morning makes very clear it has components that deal with where in history we are right now and where humanity wants to go or is drifting to at this point. But it's a straightforward problem. Whereas adaptation takes very, very many forms, from moving away from shorelines or rivers to changing your cropping systems, changing the design of cities, and so on and so on. And we don't know enough about the adaptation, how to adapt, and how best to adapt. And it's also extremely difficult to measure progress and adaptation, because in order to see whether you've adapted well or not, you have to await the next disaster. So mitigation, straightforward. Adaptation, the science, is quite different. So one of the questions that we need to address this afternoon is when the policy or when the politicians talk about defined limits, 1.5 degrees, 2 degrees, is that really a threshold that we're looking at, or are effects already here? Is the severity and the incidence of these effects a linear function of temperature increase? Is it a curve function? Is it asymptotic? Are there thresholds? And are there thresholds of no return, after which, for instance, one of the doomsday scenarios is that temperature rises sufficiently to basically melt the permafrost in the northern part of the northern hemisphere. Within that permafrost is trapped a huge amount of methane. That methane comes bubbling out. Methane is a very powerful greenhouse gas, and we're basically into a positive feedback cycle that becomes totally uncontrollable. So these are all considerations that we need to get to grips with when we think about limits to climate change and temperature change. So because of these dangers, these are, again, all pronouncements that come out of the convention and their scientists. 2 degrees should be a strict upper limit. Once we go beyond that, we are in very dangerous territories. That is the basic conclusion. That is the scientific consensus now. But there's also an increasing consensus that from 0 to 2 degrees, or from 0.8, where we are now, to 2 degrees, there are already increasing costs of disasters, of lost crop production, and so on. So the idea is to limit as much as possible. The way to limit as much as possible was a first pronouncement at Paris, saying that making this 1.5 rather than 2 has many benefits, and it probably reduces the cost that, for instance, the Stern report put out, where basically Stern said that the cost of not acting on climate change is going to be tremendous because of the damage done by climate change, and is going to be much greater than the cost of mitigation and adaptation. One of the arguments that was very, very strong is that a principal component of mitigation is to get away from the fossil fuel carbon. I'm not sure that everybody is aware of what it means and why. Biofuels, everybody knows what it is. We want to use biologically produced carbon in our cars and so on. Now, they emit as much CO2 as any other engine. In fact, because they're running on alcohol that has a lower energy content than petroleum-based, crude oil-based fuels, they're emitting more CO2 than any fossil fuel-driven vehicles. But the difference is that the carbon that we're burning there and releasing into the atmosphere the year before has been sequestered from the atmosphere through photosynthesis into sugarcane or into some other plant, then turned into alcohol, which we burn in our car. That is released. So over the 2-year span, there is a zero impact. Whereas the carbon in the fossil fuels was fixed by a similar photosynthesis millions and millions of years ago. And that is essentially, in today's carbon economy, an additional carbon. So the biofuel carbon cycle is a true cycle where we capture carbon from the atmosphere, release it back into the atmosphere, and that is what we call carbon neutral. So a big consideration, of course, is how do we distill the alcohol? Do we use fossil fuels to do that? And there are many details that need to be discussed there, but basically the idea is to go to renewables, which is solar, which is wind, and which is bioenergy. And one of the arguments is that biofuel can compete with the production of food. As I mentioned yesterday, I will hopefully always be in a better position to put a tank full of fuel or fill up my car with biofuel than the poor person in the northeast of Brazil or somewhere in Africa will have to put food on his plate. These are social inequities that we need to deal with, that we need to consider, and therefore the question of biofuel is not just simply one of technology, but also one of ethics. And the issue of ethics we discussed yesterday, and it came up this morning again. But the counter-argument that if we go much beyond 1.5 degrees, and that I will show you after Inés's talk, there will be very, very major impacts on the possibility of adequate food production, so that finding an adequate policy and substitution for a policy for biofuels is the better choice, particularly if we go into third-generation biofuels that don't compete as much with agriculture. Now, many years ago, I actually made it into almost every daily newspaper in Argentina because I gave a talk to a large agricultural convention in Argentina, and I said, leave the maize alone because people want to eat it, and don't use it for biofuel. And of course, the biofuel producer said, oh, this is the old story that we've heard many times before, and the guy is retrograde and whatever. But let's face it, maize has been selected over thousands of years for its high protein content, for its high nutritional content. In order to produce a grain of maize, we need to put nitrogen fertilizer on there in order to get a decent protein content. And then if we produce that maize only to capture the carbon, to burn it in some machine, makes no sense. So really my argument was not so much against was not at all against biofuels. It was just against using a crop that had been selected for a high nitrogen content only for its carbon content. So we need to distinguish some of these industrial processes along the way. So the recent science policy discourse, therefore, is 2-degree limit, absolute maximum. Beyond that, we don't know what's going to happen. 1 is pretty good, maybe, but we're already beyond, or 1.5 is pretty good, but we're already beyond the point where we can stop at 1.5. It's becoming more and more clear from scientific evidence that we will go beyond 1.5, and then the policies should focus on trying to come back down to 1.5 at the end of the century. What the trajectory is going to be from here to then are very many political decisions. And that's really the key of this discussion, that what kind of policies we take as this thermometer rises is something that democracy, that capitalism, that different economic and decision-making systems need to determine. And I put this on, and I saw in Inés's talk, she had the same one. I took it off the BBC webpage, and it says Paris without the US. But as I said, I don't believe that, because the moment the US federal government says that they are going to not honor Paris, California comes up and says, but we will, and New York will, and so on and so on. So there is going to be a impact that is much less of a US impact. Now, this is also pretty pessimistic. The current pledges, we will get to 3.3. If we get to 3.3, we will have a serious problem. So it's important to realize the granularity of this. Global averages, everybody probably remembers the scandal just before Copenhagen, when somebody hacked into the server of a UK university and released the emails that the climate research group had exchanged that it was evaluating the global temperature increase. Because they were saying, well, they were cooking the data, they were manipulating the data. I also downloaded these hacked emails from WikiLeaks and had a look at some of these emails, and to me it was a very different picture. It was a group of scientists desperately trying to make sense out of climate data, out of recording stations somewhere in Siberia, others somewhere in Africa, some recording stations where you know the guy never goes out to read the instrument when it rains. I mean, we know in developing countries and in many countries how meteorological stations work or don't work. So they were eliminating data. They were trying to do their best, and they came up with some kind of a consensus on what the global mean would be. And within that, of course, it became very, very clear that there are huge differences in climate change between, say, Siberia and Africa and Central Europe and so on and so on. So mountain areas, high latitudes closer to the poles, they show much greater impact, much greater temperature change. Islands are much more threatened. Transitional zones will change, and I will come back to this. And it is absolutely vital that that granularity become captured in the political decision making. When this morning we talked about should there be a world kind of UN government for everybody, I don't agree, because it's not going to work. We know that decision making at a global level is not going to work, because the person who sits in Berlin will not be terribly concerned about what happens to the glaciers in Bolivia and what happens to the glacial outflow that washes away another village in Bolivia or in some of the tropical Andes. So we need this connectivity between regional and global. So the questions on both mitigation and adaptation is, we're talking about means, but how meaningful are means? The concerns are extreme event, not means. So how do we relate these? Is climate change really reversible at human scales? There has been climate change in the past, but it's been 20 million years ago. We don't want to wait 20 million years for humanity and this society to recover from an effect. At what level do irreversible changes like the bubbling out of methane from Arctic soils, and where does it become irreversible? And I think in order to understand some of that, we need to understand some of the basic climate science, which I don't know.
Well, hello, good afternoon, everybody. My talk is about, as Holm mentioned, about the 1.5 world. And first of all, I'm Inés. I'm a climate scientist. I'm professor at the University of Buenos Aires, and I also work in these other institutions. And my background is also in atmospheric sciences. So This is, oh, there's a problem with the outline of the presentation that is not working, but I can tell you what we are talking about. We will talk about the Paris Agreement and the United Nations Convention on Climate. We will also talk about the relation between CO2 and global temperature, and some of the impacts related to these different targets of warming, and at the end some conclusions. But during this talk, we will also talk about maps. We will see lots of different maps that we were talking about, some challenges about climate change also, and some ethical discussions related to climate change too. So, what's the United Nations Framework Convention on Climate Change? First of all, it's a global instrument. It comes from an international agreement that the main goal of this is to control and to manage the emissions of greenhouse gases. It was adopted 35 years ago. It was in this context when the 2 degrees warming was established as a dangerous level of warming for the world. And this convention entered into force in 1994. And which is the status of participation? In the language of the convention, we do not talk about countries, but instead we use the term parties. So up to now, the convention was signed by 197 parties. That it has one regional economic integration organization. This is the European Union, and all the others are really different countries of the world. So the overall goal of this convention is to protect the climate system in the context of sustainable development. This means to protect not only our generation, but also future generations. And the further objective is related to achieve a stabilization of the greenhouse gases concentrations to prevent dangerous anthropogenic interference with the climate systems. And here is where it comes, this 2 degrees warming, this target of 2 degrees warming, defined as a dangerous warming for the world. So, what is the conference of the parties associated to the Convention on Climate Change? First of all, is the supreme decision-making body of the Convention, where all parties agree by consensus or decisions. They do not vote to adopt something. It's everything is decided by consensus. And the main task of this conference of the parties is to review the national communications of the different countries. These national communications include the greenhouse gases inventories that they submit, each party submit to the convention, and they assess the progress of the emissions of the different countries. And the COP meets every year in different cities of the world. The first one was held in Berlin in 1995. So the Paris Agreement was adopted in one of these conference of the parties in December in December 2015, and they adopted 2 long-term global goals. The first one was to limit the warming well below 2 degrees, always considering the pre-industrial period. And the second goal was to pursue the efforts to limit this warming to a more ambitious goal to 1.5 degrees, considering that this second goal would prevent this dangerous interference of the CO2 concentrations with climate and the associated impacts. And also, this Paris Agreement decided that each country should present these national determined contributions where they, in some way, voluntarily offer the reductions of the greenhouse gases emissions they can do during the next years, just to limit the increase of the CO2 concentrations in the atmosphere. And every country has to present these contributions. They can change the contribution every year before 2018, but always to a more ambitious goal of reduction of the reduction of emissions. And after 2018, they can change these contributions every 5 years. There will be a stock take of all the contributions, just to assess the collective progress and efforts to reduce the concentrations of greenhouse gases in the atmosphere. Well, this agreement was ratified in November 2016. And this is one of the maps we're going to see that reflects the status of this Paris Agreement, the countries or the parties that ratified the agreement, the countries that just signed the agreement but they do not ratify it, and those countries that didn't sign or withdraw from the agreement. As you can see, most of the countries, most of the parties ratified this agreement. We have only 3 countries that are out of the agreement for different reasons for these 3 countries. In the case of Syria, it's because of the war they have. They have probably many important things right now before thinking in this agreement. The second country that didn't sign this agreement is Nicaragua, but in this case it's because they considered that this agreement was not ambitious enough to solve the problem of climate change. And, well, as you know, the United States withdrew from this agreement. So if you consider the same map, but in terms of emissions and the volume of emissions of CO2 in the atmosphere, this is the situation we have. And if we separate the countries in developed and developing countries, this is the way that the convention works. We have 2 different groups. They don't call these groups developed and developing countries. They are Annex 1 countries, the developed ones, and non-Annex 1, the developing countries. So in this case, we have inside this agreement China, that is the first emitter up to now in terms of volume. 28% of the CO2 emissions right now are coming from China. The second place is occupied by US. 16% of the global emissions come from the States. They are now running out from the agreement. And you see all the other countries. In any way, it's not so fast that US is going out of the agreement. After you sign the Paris Agreement, you must be inside for 3 years before you can say, I'm leaving this agreement. So it was announced, I think it was a month ago, that US is going out, but they can effectively go out from the agreement only 3 years ahead from now. So Holm already showed this, the different targets we have associated to climate change and the efforts the convention is making to limit the emissions of CO2 to the atmosphere. And you can see we have the most ambitious one, this 1.5, and the 2 degrees warming. We have between here what the convention wants to limit the warming between these two targets. If we consider all these national contributions of the different countries, it is estimated that up to now the warming will be 3.3 degrees. We are pretty far from this 1.5 or 2 degrees with all these contributions the different parties are making. This is the estimated extra warming that is added if we consider the states out of the agreement. And this is the warming that it is estimated we will have at the end of the century, considering the business as usual. If we continue emitting CO2 and the other greenhouse gases as we are doing now. So from here we can think that during the next decades we can have 3 different worlds in some way. A world with a warming of 1.5 degrees, 2 degrees, and a warming near 4 degrees warming associated to this business as usual. So let's see what this means, this 1.5, 2, and 4 degrees warming. And this is what you can see in this map. This is the warming associated to a global warming of 1.5 degrees. And what you can see is that the warming is different regionally. We don't have the same amount of warming in the world. Continents are expected to warm faster than the oceans. And you also can see that we have these dots. This is what we call stippling. And this means that this warming is statistically significant. This means that all or most of the global climate models we use to make these projections agree in the sign. This means this warming. And also they have a good agreement in the amount of warming. But this 1.5 word means that for some regions, mainly in the high latitudes of the northern hemisphere, warming could be up to 3 degrees. And the same different distribution, we can find it in precipitation projections. Regions where you have these green and blue colors means an increase in precipitation, and yellow and red means a decrease in precipitation. In this case, you can see that these projections shows increases in those regions that are already humid regions, and a decrease in those regions that they are already arid regions. And this morning you were talking about that rich are getting richer and poor are getting poorer. The same applies not only in terms of money, but also in terms of water availability, according to these projections. And things are getting worse if we consider 2 degrees global warming. Again, we see that continents will become warmer than the oceans, and the high latitudes of the northern hemisphere will be even warmer. In this case, we are talking about a warming of more than 5 degrees. the distribution of precipitation increases and decreases is similar to the 1.5 degree world, but the magnitude of the changes are larger in this case. And you can also see that in some places we have these dots. This means the agreement in the projections. But there are some other places where you can see we have some kind of lines. This is the hatching. And this means that the agreement in that places is not good. So we have larger uncertainties in those regions. And this is the forward. If we consider the business as usual, this is the way where we are going now with the present emissions. And you can see the pattern is almost the same, warmer continents than oceans, largest warming in here, in the northern hemisphere, in the higher latitudes. In this case, the warming is above 10 degrees Celsius. And here are the projections in changes in precipitation, increases in some regions, and decreases in some other regions. So, what is the relation between CO2 emissions and global temperature? And you can see that if we can first consider the projected warming, consider these two scenarios. This is in some way, the more optimistic scenario. Is associated to lower emissions. And this is the more pessimistic scenario. It's something like the business as usual I mentioned before. But in any case, we are talking about warming that is above the 1.5 degrees, this target that we are interested to. Only this more optimistic scenario, the RCP 2.6, in some way predicts that the warming at the end of the century would be around 2 degrees. And in the case of the RCP 8.5 scenario, we're talking about a warming around 4 degrees, as I mentioned before. So this is what I wanted to show. This is the relation between temperature and CO2 emissions. And this graph is very interesting because also it shows that temperature increases as we have more CO2 emissions in the atmosphere. The relation is linear, and this is good because at least we know how temperature or global temperature is related to CO2 cumulative emissions. And why is it good to know this relation? Because this allows to fix a global temperature target and associate in some way this target to a total emission of CO2 in the atmosphere. This means that if our target is 1.5, we know how many CO2 there can be in the atmosphere for that target. And the same if we consider 2 degrees, we also can know the target as the CO2 concentration or emission associated to this target. So if we consider that this is the total carbon budget we have for the 2 degrees warming, and what we know now is that 65% of this budget, we already use it. So we just have this amount of emissions available before reaching this 2 degrees warming. So what this shows is that the window for action, if our target is 2 degrees, we have even less time if our target is 1.5. we need to act quite rapidly. And this graph shows, if we consider the emissions at, just as they were at the beginning of this year, at the beginning of 2017, we can in some way compute how many times do we have before reaching the different targets, 1.5, 2 degrees, and 3 degrees in this case. And what we can see from here is that if we consider this target, 1.5, we have, considering from the beginning of this year, just 4 years before reaching 1.5 global warming, always compared to the reference period, the pre-industrial period. So this is why we do not have many time to act if we want to reach this limit of warming. So we'll see some of the impacts and the avoided risk associated to this target if we compare to the 2 degrees warming. And this is important because during the Paris Agreement, some countries, mainly the countries in Africa and the small islands, they push the agreement to this more ambitious target of 1.5 compared to the 2 degrees. And this is why it is important to show the avoided risk between, if we can limit the warming to 1.5 compared to 2 degrees. And to do that, one of the ways to present risks associated to climate change is considering this RFC, the reasons for concern. This is the way the IPCC also shows this risk, because it's an easy way to communicate risks associated to different levels of warming related to climate change. And to do that, there are 5 reasons of concern that are important to see if they change with different levels of warming. The first is related to glaciers, coral reefs, ecosystems. The second reason of concern is associated to risk derived from extreme events, of weather events, heat waves, heavy rain, droughts. And the third one is related to impacts that affect particular groups because of the uneven distribution of the impacts of climate change, mainly associated to different vulnerability or exposure to the hazard associated to climate change. The fourth reason of concern is or can be evaluated associated to a metric that can be aggregated, for example, monetary damage, number of species that of extinction, or lives affected, for example. And the fifth reason of concern is associated to some impacts in systems that can be irreversible. For example, the melting of the ice caps in Greenland or in the Antarctica. So here you can see for these 5 reasons of concern I mentioned, the risk associated to climate change. And here you have the global mean temperature change. So we are mostly interested in this target, 1.5 and 2 degrees. And one thing we can see that for 1.5, we still have at least medium risk associated to climate change. And if we consider this 2 degrees target, the risk increases for all these 5 systems. So one of the challenges for science is to precisely quantify the difference on the impacts for these different systems associated to these two different warming levels. Because with this, we can compute which are the risks we are avoiding if we can reach this more ambitious target of 1.5 compared to 2 degrees. For example, if we consider the first of these reasons of concern, for example, associated to coral reef degradation, we can compare the amount of these reefs that are at risk if we consider a warming of 1.5, the blue box, or 2 degrees warming, the red box. And what we can see that if we reach this warming of 2 degrees, almost all of the coral reefs will be at risk. We can avoid some of the risks, at least limiting this warming to 1.5. The same we can see if we consider these extreme events associated to precipitation. This is the increase in intensity in precipitation at global scale and both at regional scale. For example, if we consider South Asia, in both cases there is an increase of the risk if we consider a larger amount of warming. But this is something that Holm mentioned before. There's not a linear relation in the increasing of the risk. It's not the same if we consider just 0.5 degrees of warming. And what we can see here is that for some regions, for example in South Asia, the impacts are even larger if we compare to the global scale. This is why we need this regional information just to know the impacts and how to avoid the risk associated to these levels of warming. And we can also see some other extremes associated to climate, considering these indices. These are associated also to precipitation. In this case, this index reflects the dry spell length, and in this case, we are considering heavy precipitation events. And in this case, we can see the impacts of these different levels of warming, considering 2 degrees, 1.5, and the difference between 2 and 1.5, but with a more regional point of view. And what we can see is in the blue regions an increase of these extreme precipitation events. Some of these regions have a lower risk if we can limit this warming to 1.5, and here you can see the difference. For example, Southeast Asia, the region I mentioned before, is one of the regions where the increase in these extreme events are projected to be more important. And here we can see the effects of the other side of the distribution, the dry spells. And we can see that in some regions, the increase of days that belong to a dry spell increases in some regions very dramatically if we compare the 2 degrees warming to the 1.5 degrees warming. So differences between these two targets of warming are related to really different impacts if we consider the regional scales. We can also see these impacts considering extremes, in this case in temperature. This is for the intensity of hot extremes. This means the annual maximum value of the daily maximum temperature. And in this case, we have the warm spell duration. Again, we can see the maps. this is in the case of the daily maximum temperature in all the continental regions where we have measures of this maximum temperature and where it's more relevant. We see that there is an increase that is above 3 degrees for the 2 degrees scenario. And there's a reduction of this increase in the extreme maximum temperature if we consider the 1.5. And in the case of the warm spell duration, we find that in the same, almost in the same regions where we have these longer dry spells, we also have an increase in the warm spells. So there are regions that are threatened by not only by very hot days, but also with mainly water availability problems because of the hot days. And the third reason of concern was associated to this uneven distribution of impacts if we consider some regional effects. In this case, if we look at the water availability, this is the case in the Mediterranean. In both cases, for both scenarios, what we expect is a reduction in water availability, but this reduction is more dramatic, again, in this 2 degrees scenario. And this led us to identify some regions that we can call these hot spots that can be particularly threatened by the impacts of climate change. So this is a table that in some ways summarizes the different impacts associated to these 2 targets of warming, associated to extremes in heat, the heat waves, the reduction in water availability, increase in heavy precipitation. These are the results I show you in the maps before. And here you have the expected increases in sea level because of these different levels of warming. In both cases, at the end of if we compare the sea level rise projected under these 2 scenarios with the sea level for 2000, the expected sea level rise is around 40 centimeters for the 1.5 scenario and 50 centimeters for the 2 degrees scenario. The numbers you have here are the uncertainty we have with these figures. And this is the rate of the increase of the sea level. Also consider these 2 scenarios. And this is the fraction of coral reefs, as I showed you before, if we consider also these 2 scenarios. For the 2 degree scenario, it is expected that coral reefs will be seriously in trouble. So, how can we reach this 1.5 target? It seems that it's in some way much better than the 2 degrees target, but how can we go to this value? And for that, it's important to consider this, what we call the overshooting. This means that it's expected that to find a stabilization target to reach this 1.5 degrees warming, during some time there would be an overshooting in the concentrations. This means that warming associated to these concentrations will be above this 1.5 degrees Celsius. So the climate impacts associated to this overshooting in the carbon emissions will be associated to the magnitude of the overshooting. We have here 3 different examples of the overshooting, from a small overshoot to a large overshoot. And it depends for how long it lasts, this overshooting. It's not the same to have a large overshoot, but during a short period of time, or to have a small overshoot, but that it lasts during a long time. And this is the situation we have. You have here the global mean temperature increase in considering our reference period, the pre-industrial time. And considering these three scenarios, the business as usual, in some way, this RCP 815 that leads to this warming of the world. The more optimistic scenario, the 2.6 RCP, that leads to this projection, but as I mentioned before, it's above the 1.5 target. And if we consider another scenario that leads to this 1.5 degrees global warming. And what we can see here that even for these two scenarios, the RCP 2.6, this optimistic scenario that was considered by the IPCC in the last assessment report, or even this 1.5 scenario, for those, for both of them, during some period of time, temperature will be, global temperature will be above this, the global warming will be above this 1.5 target. This is what we call this overshooting that I mentioned before. And as you can see, it seems that in some way we cannot avoid this overshooting, at least during this century, if we want to reach this 1.5 target. So what does it mean, this overshooting? That if we want to reach this 1.5 degrees warming, at least at the end of the century, this graph shows the greenhouse emissions. This is the business as usual. This is the RCP 2.6, and this is the scenario, this one, the light blue, that is related to 1.5. And as you can see, here we have negative values of the emissions. What does this mean? This is what we call the negative emissions. This means that in some way, we do not have only to limit the emissions to the atmosphere of CO2, but in some way we have to remove CO2 from the atmosphere. How can we do that? With human intervention. We are still acting on climate if we want to remove CO2 from the atmosphere. And this is the different pathways we have. These 4 pathways are the pathways that were considered, as I mentioned before, in the IPCC assessment. The more pessimistic in some way, the 8.5. This is the 2.6, and even the 2.6, the RCP 2.6 scenario means we include some negative emissions to reach this target of global temperature between these two values. This reflects the uncertainty we have in the projected temperatures at the end of the century for each of these scenarios. So how can we do that? How can we remove CO2 from the atmosphere, these negative emissions? One way is what we call deafforestation and reforestation. These are examples of these two different processes. Reforestation means to plant trees in a place where previously there were trees and it was deforested. And afforestation means to plant trees in a place where time ago there wasn't any tree. Another way of negative emissions to remove CO2 from the atmosphere, it is considering bioenergy to produce biofuels. And we can use these biofuels, as Holm mentioned before, for energy. But this technology that it is called BECCS means that the CO2, instead of being emitted to the atmosphere, is captured, and then it can be stored in rocks, for example, in the land. So, yes.
What is the energy source of this process?
This
and the energy cost of this process?
Of this process, it seems it is supposed to be good enough that the budget would be negative in terms of CO2 emissions to the atmosphere. It depends on the time you consider for the budget, but it can be 1, 2, or 3 years that it would be enough to remove, to have a negative CO2 balance in the atmosphere associated to this.
So you need clean energy to produce this process?
You use these biofuels, yes, to use it in the industry, for example. And instead to release the CO2 to the atmosphere, you capture and you inject it in the ground. This is the idea of the BECCS. So, is it good to think about afforestation as ways to remove CO2 from the atmosphere? And this is an example of how it works, this process of reforestation or afforestation. If we consider changes in the albedo, for example, and associated to these changes in the albedo, the net radiative forcing associated to this. So you can see that in some places we have negative values. This means that negative emissions could work in that regions if we consider these reforestation or afforestation processes. But in some regions where we have these positive values, these ways to produce these negative emissions are not good because they are related to an increase in the radiative forcing. So this means that in some regions, to think about reforestation or afforestation as a good way to solve the climate change problem is not a good idea. It works only in some regions of the world. We cannot think about planting trees all over the world as a solution for climate change. Yes? This net radiative forcing in some way is a measure of the energy balance of the system. Where you have positive values, it means that in the Earth system you keep more energy than the energy you release to the outer atmosphere.
It's simply that, for instance, if you look at canopy color, look at the color of a coniferous canopy from space, it's darker than what was there before. A darker surface absorbs more energy, and therefore afforestation in those regions would have a extra energy capture effect, which is what you want to avoid. It simply is the color of the land cover that causes the extra energy to be captured.
Yes. Positive values means that you keep in the climate system more energy than you get back to the outer space. That's why it means warming, because you keep more than you get back. And in some regions, it could work. And associated to the other way of these negative emissions. This means to use bioenergy and to capture this bioenergy and inject the gases in the ground. It also had some uncertainties associated. One of them is related to, in some way, the competition in the land use. If you use land to produce these biofuels or to produce food, this is one of the questions that is still out there in the scientific community and also in the society related to this way of removing carbon dioxide from the atmosphere. Also related to the cost associated to this technology. It can be very expensive in terms of the amount of CO2 we had to inject in the ground. And also it had some social barriers, such as the public acceptance of this kind of technology, to use this kind of technology. And other way that is not associated to negative emissions, but in some way that could be useful to cool the planet, is what we call the solar radiation management. This means in which way we can reduce the amount of solar energy we receive and that is retained by the Earth. And to see the effects of this kind of intervention on climate, there is a project that they use climate models and to quantify in some way the effects of this intervention, this geoengineering. We'll see results associated to this solar radiation management. And to do that, we will compare if we increase abruptly the CO2 concentration in the atmosphere compared to the pre-industrial. We'll see the climate that we will have under these conditions, to the climate that will be associated if we manage this solar radiation in some way that we can reduce the amount of energy we receive from the sun. And to do this, they consider 12 models, and the reduction on the solar energy is about 3.5 and 5%. These are the results. With this increase in the CO2 concentration, what we find is a general warming. And if we consider this solar management, mainly if we reduce in the same way, not with difference in different latitudes, but in the same way globally, the solar radiation, this is the changes we find in temperature. You see that some regions get warmer, and in some regions get cooler. We cannot offset the effect of warming associated to this increase in CO2. And these differences in warming or cooling, in temperature change, shows also differences in precipitation associated to this geoengineering management. What we can see if CO2 increases abruptly, we have some regions with an increase in precipitation, some regions with a decrease in precipitation. But globally, this means a reduction of 4.5% if we consider this kind of radiation management. And mainly the reduction, you cannot see here because this is written over the map, but the reduction is mainly in the tropical regions, and this is associated to this cooling of the regions. those regions were due to this change in the solar radiation that are associated to cooling, also are associated to a reduction in precipitation. So, at least if we consider this kind of geoengineering, that it means solar reduction that is uniform all over the world, we cannot go back to the previous climate. Yes?
What is the geoengineering that was proposed in this study?
You can inject aerosols in the atmosphere to reduce the entrance of solar radiation. This is one of the ways to do that. But in this case, it's a uniform reduction. It's an experiment with a climate model, or 12 climate models. But what we show is that even if we consider as an option this solar radiation management, what we can see that we cannot go back to the pre-industrial climate, and we still can find differences at regional scale. So today or this morning, the discussion was about technology as an option for climate change. At least geoengineering is not an option if we want to go back to the pre-industrial climate. So just to finish my presentation, some conclusions that are more questions that you can keep them in mind for the discussion we will have late this afternoon and tomorrow. We have some challenges as a scientist. What we need to address is, or to do, is to quantify impacts at local scale. We have an idea of global impacts, but at local scales, we need to quantify them associated to these 2 degrees warming. Also, we need to quantify at the local level the differences between the 2 degrees and the 1.5 target. We don't know really the consequences of, we can limit this 0.5 degrees warming, the impacts at different regions and different sectors. And we also need to identify which of these impacts will require adaptation and what will be the cost of this adaptation. As a society, we also have many challenges. First of all, we need to agree what risks are acceptable for us. We need that climate is changing, and it will continue changing at least during the rest of the century. We need to agree which of the risks associated to climate change are acceptable for us and which are to be avoided. And this is important at regional scale, local scale, and for different sectors. And as a society, we also need to demand the decision makers to aggregate this local scale risk to the global targets, because the discussions and in the convention, for example, of climate change are related to a global target, 1.5, 2 degrees. Well, how would they consider local effects when they say 1.5 is acceptable? Is an acceptable target for everybody, for all sectors, or it is not? So this means that the discussion has also an ethical point of view, because what we know that risk is high in some regions, in other regions risk is lower. And when we consider this global average, in some way we are accepting that many of us will live with a higher levels of risk than others, who says this is okay, this is worth, or we have to change in some way our point of view of this discussion. I think this is the last one. Yes, on time.
suggest we have a few questions
Okay.
and break for
Okay.
coffee then, and after that I continue.
Thank you. I think we have many options to do, but we need to think that two big players are out. United States is not in the game, and China is on the bench. They will be thinking about reduced greenhouse gases after 2030. So it's a comment.
Yeah. Well, United States is out, but the commitment was for 2025. It was not just right now. So climate change is a global problem. It needs global solutions. That's right.
Hi, Professor. In the last 2 weeks, we talk a lot about technical and technological options to mitigate climate change. But I would like to know your opinion about change in behavior to reduce the personal carbon footprint.
The individual behavior that each of us has to do that. I think it can contribute to some way to mitigate climate change. But we can also have to keep in mind that it means in some way some kind of cultural change we should have, that if we want to really see that individual contributions can be reflected in a global way on climate. We can do that, but it's not enough. This is at least what I think.
I think the solution, at least how we discuss it, is like the government are going to solve the problem for us. And I think that there is a line of thought that indeed we have to all work together. I mean, from individuals to organizations that are regional, and also governments. So what I think what we are seeing in the U.S. is that likely the states are going to really, and the civil society is going to emerge in this. Mm-hmm. So I think there is hope. I see more hope in civil society than in governments, to be honest, in the first place, because civil society is the one that really will be facing, I think, the consequences, and also the small islands, for instance. Well, they are in the first line of impacts. Yeah. So I think I see that it has to be from top-down or bottom-up approaches. So yeah. I don't know. What do you think? How do you foresee this interaction between the civil society and the government?
I think it's growing, this interaction, and in some way, maybe at the national level, it's more difficult to reach an agreement. But as most of the emissions come from cities, 70% of CO2 comes from cities, and they're increasing agreements between cities to act together to reduce the emissions. I think that civil organizations, together with these local governments, if they work together, I think this is a good option to reach these targets at least.
If there are no more questions, I suggest we have coffee, and in 20 minutes meet here again
question over there.
One question more.
Yes.
Okay. You already know that temperature varies, especially across the globe. It means that in Brazil, maybe the increased temperature can be different in Africa.
Yes.
My question is like, do you know a point in in the world if the increased temperature has already exceeded the 2 degrees? If yes, where is the impact on the population?
If the increase in temperature is over 2 degrees, I'm sorry, I didn't understand well. Did you understand?
Is there any place in the world that the increased temperature has already exceeded the 2 degrees temperature? If yes, what is the impact of the population?
This is what we need to know. This is why I said we have a challenge for science. We need to quantify these impacts at regional scale. And this is what the IPCC is trying to do, because it was one of the things that was requested by the convention during the Paris Agreement. They asked the IPCC to prepare a special report on the impacts of 1.5 degrees world. And the idea is to have a map of impacts of different regions and for different sectors of climate change for 1.5 world, and also to quantify the avoided risk compared to other levels of warming. But to do that, the IPCC needs the science to work on that, because the IPCC, what it does in their reports is to assess literature on climate change. And to do that, we need science from all over the world just to show the different impacts at regional scale of these different levels of warming.